This talk today is going to be about converting source separation models. I don't think an S should be there because we only do one model. But yeah, to ONNX, the Open Neural Network Exchange for real-time usage in DJ software, which is the Mix open source DJ software. I guess some of you met Antoine here, who's from Mix. And this project was carried out under the Google Summer of Code overview within the Mix DJ organization. And MTG is because I'm from there. Okay, so before we talk about music source separation in general, I want to talk about just this problem of source separation. Like what is source separation? And the essential idea is that you want to separate some sort of, you want to distinguish between different sets of sources or tracks within a mix. So for people who work on speech separation, they use this word for separating, let's say, 2 or 3 speakers within the same audio. That is source separation. For our case, for music source separation, that could mean if you have n number of instruments, you want to separate each of them out. In this talk, we are going to use a very particular one framework, which has become very popular recently in the academia and industry, which is to separate out music into 4 different stems. Specifically, the one being bass, which is on top in this slide, drums. The third one is actually others, so everything your synthesizers, piano, whatever it is. And the fourth one is vocals. And this is the standard framework. There are some models that do 6, so a separate one for piano and guitar as well, but we are not going to talk about them today. So for music stem separation, what is our core problem? I mean, researchers did these models, they made these nice deep learning models and released it. But we can't use them. We can't use them on our devices. We can't use them in our plugins. And we want something that can run on like Mac and Windows and Linux, and not just run on all these different platforms, but also target different hardware execution providers, which is a term that I'll dive deeper into if you're not familiar with it later in the slides. So we don't want models that run just on the CUDA platform, which is from NVIDIA, but we also want it to run on the Apple's CoreML and the OpenCL execution platform. Now, that's kind of the framework that we are going to deal with. So how to go from a research-based model to something that we can run within all these different platforms. Now I'm going to talk about the Demucs model, the very specific model that we work on in this project. So Demucs was a model released by Facebook AI Research at that time, now Meta AI, which came out as one of the best models in the original Sony Music Demixing Challenge from 2021. And there are now later additions to this model, which is one of the ones that we export in this work. But the idea is that a lot of state-of-the-art models today as well use some sort of Demucs-based foundations. So if we can export this and solve some of the problems that are there in the export in this model, we can easily deploy the newer models as well. I want you to look carefully at this diagram on the left. There's a lot of math here, or like a lot of mumbo-jumbo here for people who do not work in deep learning. I want to tell you, you can just cross out everything that's in between. And it doesn't matter for you. The only things that matter are here on the ones on the bottom and the ones on the top. And why is that the case? Because how you can think about it is Demucs as a model has 2 different channels, or 2 different mediums in which it operates in. There's one entire branch that operates purely on a waveform, so whatever your full track is. And there's another branch, this one, which operates fully on the spectrogram, which you obtain by doing a short-time Fourier transform. So for those of you who are not aware of STFTs, I'm going to dive deeper into that later in the slides. So 2 branches, audio only, and time frequency spectrogram branch. Something happens within this branch. What you get out in the spectrogram branch is 4 different spectrograms corresponding to each of the sources. And then you can just do an inverse of the short-time Fourier transform to get back the audio. That's the audio from the spectrogram branch. And from the waveform branch, you just directly get 4 different stems audio, and you add them eventually to get your outputs. So ignore everything inside, but this is what we are going to dive deeper into, and why this is the most important part that gets problematic when we start to export things. Okay, so I've been dropping around the word ONNX a lot. What is ONNX? In simple words, it's an open standard for machine learning interoperability. What is interoperability for machine learning? It's the problem that I was talking about before, that your models today are very deeply tied. The research world is very deeply tied to the Python ecosystem. And they use just very few libraries like PyTorch and TensorFlow for these works. So if you need to run them anywhere, you kind of essentially need to recreate this full Pythonic environment. How do we get away from this? That's the problem that gets solved by ONNX. You can think of it as a serialization format, so something like JSON, where you can export your model and then you can use it inside any of the languages. So if you want to make a plugin in C++ or Rust, like this is where you need to begin. Like you can't even do it unless you export your model to this. There's another very related package, or like a very related concept, but different from ONNX, which is known as the ONNX Runtime, which solves the second half of the problem, which is about not just interoperability across languages, but actually helping us use it across different hardwares and different platforms. So a lot of the models today use specifically they are optimized to run on CUDA, which is a closed source solution from NVIDIA. But a lot of different hardware providers have sort of made these their own libraries, let's say, for faster execution of neural networks. But if you want to, let's say, export your model to run on each of these, you don't want to do it for each of these individually. So how can you do that quickly? You just use something known as ONNX Runtime, which is maintained very actively by Microsoft. And it supports a bunch of different hardware execution providers in the backend. So two big problems solved for us using ONNX and ONNX Runtime. So now that I've established like why it's important to use ONNX, and I'll talk a little bit about the model that I showed before, I'm going to dive a little bit deeper into what's the core problem when you try to export this. And it's related to this third row that you see here. It's this big problem of complex tensors. And I'm going to talk about what complex tensors are, but PyTorch essentially supports something known as complex tensors, where your tensor is a matrix, and your matrix has complex numbers as an object, like as a class. But ONNX does not support that when you export these models. So you sort of need to rewrite things. And so if you do something known as the default ONNX export, which you see on the right here, the torch.onnx export, the core model here is actually this Demucs model that I tried to export. Look at the error that you get below here. Like error during ONNX export, STFT does not currently support complex types, which is essentially complex numbers. And so if you see these two red highlights that I made, these are the two operations that use complex numbers. As you're very well familiar with audio, for Fourier transforms, like they use complex numbers. This is not so much a problem in images, which is where most of the deep learning, let's say, originates from, most of the algorithms, and then we adapt them to audio. So we run into this problem again and again. And so the hard truth is that we need to individually look at each model and see where this has been used and then rewrite it. So this is essentially what we ended up doing in our work. But it was, and the fact that it's one of the state-of-the-art models now means that we've solved this problem of actually being able to do source separation with ONNX on different architectures and platforms. How do we do that? How do we actually export these? How do we solve this problem? So before diving into that, let's talk a little bit about short-time Fourier transform. For those of you who are not so aware of why STFT, how it works. So this is your audio signal. If you look at the top, this is where this is your entire track, let's say, which has all these different sounds, or any song that you like, which you want to separate. When you do a Fourier transform, you can do a Fourier transform the entire track, but that's not very useful. What you do is something known as a short-time Fourier transform to get temporally relevant local information from each of these windows that you see here. So these windows, these triangular windows that you see here. And we hop or like jump so each of these windows corresponds to like one frame, and you're hopping across them with the hop size L. So these windows, then you do an normal Fourier transform for these to get these Fourier transform curves, and then you stack them all along the time dimension to get a matrix. Is it a 2D matrix? Is it a 2D matrix or a 3D matrix? It's a 3D matrix. Where does the third dimension come from? It's the complex number, yeah. The third dimension has the complex number, and there's 2 numbers in there. Now, one of the reasons, and we got really lucky with Demucs here, that we could do this easily, this rewriting, without changing any of the middle layers here, is because Demucs ignores the phase. And a lot of audio source separation models will ignore the phase. Not true for all of them, but a lot of them do. So once it ignores the phase, we were sure that nowhere inside this network does it use a complex number. It uses STFT, it gets a complex number output, but it reduces it back to just the magnitude spectrogram and throws out the phase. And that's why we got lucky. Just to give you an intuition why phase spectrograms are not used, if you look at on the right, this is a speech signal, but this is how this behavior is across any normal signals. Look at the magnitude spectrogram. It gives you a very detailed information of how frequencies information varies with time. And look at the phase spectrogram. It just looks like noise. And so a lot of times you don't get very useful information from the signal. So that's one of the reasons why, that's a little bit of intuition why you can ignore it. And so that's what they did in Demucs. And because they did it, what we could do was just rewrite the STFT and the ISTFT operations and make that ONNX exportable. So I'm not going to dive deeper into the math of it. There's a very detailed blog post that I have that I'm going to link at the end of the slide. So if you want to read the math, you can read that. It's not very complicated. It's just re-implementing the complex operations as 2 different real number operations. But in this case, I want to show you let's say this shape changes, because in any deep learning model, around 80% of the work is getting the shapes right. So this was the spectrogram function, the original Demucs code from Meta AI. And they were using this call, which is the TH is for torch here, torch.stft, short time Fourier transform call. And what they were getting out was a 3-dimensional matrix. This first one was for batches. So it's you can ignore this. But these were the 2 that's important. So actually a 2-dimensional matrix, not a 3-dimensional matrix. Why were they getting a 2-dimensional matrix? Because in their 2-dimensional matrix, each of these cells was actually a complex number object. So you did not need another dimension to represent them. And that is the problem as well. Like that's the problem. That's what ONNX cannot use. So what we did was we added another dimension. If you see on the right here, we now have frequencies, frame, and dim. Dim is literally another dimension for splitting my complex number into 2 different real numbers. And dim always has to be 2, so that's just an assert check for that. The real implementation that we do, where I split the complex numbers and operate on just the real parts, happens inside this function call, but I don't want to dive so much into that here. Just want to show what's the key idea. And same for the inverse spectrogram, where we have this ISTFT function, which essentially initially operated on a complex spectrogram. So I wrote this comment here on the right, I think. Yeah, it was a 5-dimensional tensor, and 5 dimensions, the first to come from the, not too important, but the idea is that now what we use is a 6-dimensional tensor, where we add another last dimension with a shape of 2. So again, splitting a complex number into real and imaginary parts. And getting the same behavior down, where once you do the ISTFT, you do it on these complex and real parts separately. And you get the final waveform out. So just by rewriting these 2 operations, we were able to make the original Demucs code exportable. Some of the previous works tried to do it by bypassing this problem of actually just removing the STFT and ISTFT from the model and choosing to rewrite it in any of the languages that they want to re-implement in. But you could see how that is problematic, because first of all, you need to ensure numerical consistency in your STFT and in your implementations in different languages. And the second big thing was actually the hardware acceleration, because once you do not export it as part of ONNX, you cannot use any of the hardware accelerations. So we solved both of these problems, and this work was the first work to actually do this. So now that I've talked a little bit about what what technical parts we did, let's zoom out a bit and see what was the output like? Because we did rewrite things, right? So we might expect a little bit of numerical differences in our rewritten operations. So these are two anecdotal examples of a track that I passed through the ONNX model and the PyTorch model. And you see these are not fully overlapping, but pretty close. And this is for like the base stem of one of the tracks. This is for the other stem for one of the tracks. But this is not the best way to evaluate, right? This is not very, you can't just anecdotally keep on throwing tracks and trying to match these numbers. So what we do is a very scientific test, which is known as the MuseDB test, which is used by researchers for this problem, where we benchmark our exported ONNX model on this MuseDB test set. And we observe the performance numbers for these different stem categories. So MuseDB tested has like 50 different songs. So it's I think 3.5 hours, a very long data set. And we observe that our separation quality is very, very closely similar to the original. So it's not just that we managed to export it. We also managed to export it to a very high degree of numerical consistency between the original and the exported one, which is a big problem with exporting or source separation, exporting any models in general, because a lot of times you get a significant drop in your performance once you export it due to numerical inconsistencies. This was achieved by writing very particular tests while I was exporting these, while rewriting these functions. All of that, which has been detailed a lot more in the actual blog post. So a little bit on the performance side as well. I'm not going to spend a lot of time here now, but so I did few numbers with the M2 Pro CPU Apple and running purely on CPU. So the MuseDB evaluation, which is like some 3 hours something of audio, takes like 90 minutes. But our C++ ONNX, like ONNX model deployed inside C++ scripts, is around 18% faster as well. And this is not even using the hardware acceleration. This is just purely on CPUs. And on the GPUs, this is actually not correct anymore. So what I realized, this is also faster because these numbers actually come from Python implementation of the Python usage of ONNX. And Antoine here, who reran these tests with Rust and ONNX, observed that it was actually faster here as well. So yeah, we achieve like faster results and like portability across hardware. So I think yeah, that's and even for GPU cases, like CUDA is very well optimized for NVIDIA. So even if the old numbers were like not that, let's say, not that much improvement in performance, you still get the same consistency in the model that you've exported. Now you can deploy it with any language on any different platform and you still get the same numbers. So I want to give a final shout out to Antoine, who deployed this ONNX model again inside another Rust tool, where you can actually just use it to separate your audio tracks live. And the other one is the big issue where we are trying to integrate this exported model inside the Mix DJ software. So hopefully by next year, you'll be able to actually do real-time DJ source separation inside Mix DJ. Not super important, just a wrap up of what the things that I said. And finally, this is our repository, and on the right is the big blog post where we go into a lot more depth about how we did this. So yeah, thank you so much.